Now, in 10th standard, you have been used this concept of probability in mathematics, and it is one of the advanced topics which is being used in everyday life in computations, and therefore we'll have to study this topic once again, little advanced level, not completely, because probability theory is a big topic. We will study it at a little advanced level and try to solve complicated problems, maybe beyond the level of IIT Advanced. And therefore, I will just first perform one experiment, and then we will run through the basic theory of probability, and we will solve problems and learn how to solve problems. Okay, the question is now what is going to happen is I am recording and you all will be visible in that recording. So I can't avoid that because I have some questions for you whose answers are required. So question is, if I have two pens with me, normally we have markers, but suppose I have two pens with me. One, this pen I use for writing on graphic tablet, does not have ink, it just without ink pen, and this is my regular pen. I use this for writing my notes or solving problems, or solving or writing corrections in mails. Okay. Now, if I give you these two pens to you and ask you a question that give me one of the two pens with 50% probability. Okay. Suppose these pens are with you and I ask you to give me say writing pen or electronic or ink pen, give me one of them with 50% probability. Will you be one of the two pens with 50% probability, and how will you give me? Shall I pause and ask you to think a bit? Unnecessary recording. Question was how one will give me an ink pen or an electronic pen with 50% probability. Answers came from students. Just make two cheats and pick one of them. You will get 50% probability for that pen. Or if head comes, you get ink pen. Decide like that beforehand and toss a coin. You will get the desired result with 50% probability. If we want to have say 70% probability for getting the ink pen, you make 7 cheats for ink pen, 3 cheats for electronic pen, mix them randomly and pick any one of them. You will get ink pen with 70% probability. You can always design an experiment which will give you the desired probability. Okay, so this is just understanding how the probability term or how the probabilistic calculations are going to be useful to us in real life situation. So the idea of studying probability is to understand these things, and there is a whole lot of theory behind probability. We will study only that much theory which is required for us. Okay, let us begin. So there are many terms which we should be aware of, and many of them you are already, because you have studied this in 10th standard, but I will just write down the names of those terms so that in case if you really don't understand any one of them, we can write down the meaning of that. Otherwise, we go ahead and start developing the theory and eventually solve the problems. First, random experiment. Random experiment. Random experiment is an act or experiment has more than one possible results which are known in advance. and it is not possible to predict which one is going to occur, then such an experiment is called random experiment. Very simple. This experiment has more than one possible results and you cannot predict which one is going to happen, then the experiment is called random experiment. Second term is outcome. Result of
What is sir?
काय म्हणताय लिहून नंतर घेऊ नका तुम्ही. These are standard definitions and available everywhere. You should not waste time, nor I will waste time writing on whiteboard. We are just checking whether we are understanding these terms or not. Outcome, the result of random experiment is called outcome. Third term is equally likely outcomes. Two outcomes are said to be equally likely if either of them cannot be expected to occur in preference to the other. Equally likely. So, head or tail equally likely provided the coin is unbiased. 4. Sample space. The set of all possible outcomes of a random experiment is called sample space, and its elements are called sample points. So sample space and sample points. You can ask any question if you are not understood, but I think this is very simple. Event. This is important because we will have to define event for finding out the probability. Any subspace of sample space is an event. Subspace of sample space. Six, simple or elementary event. If an event contains only one sample point, then it is called simple event. 7. Sure event. An event which contains all sample points of sample space. An event which contains all sample points of sample space is called sure event or certain event. 8. Impossible event. If an event is the empty set, then it is called impossible event. 9. Complementary event. Let A be an event in the sample space S, then A is a subset of S. Consider S minus A is also subset of S and is called complementary event. So whichever are remaining, that is complementary event. Okay. 10. Mutually exclusive events. A and B are disjoint sets, then A intersection B does not contain any sample point. Therefore, A intersection B is empty. Number of points in A intersection B is equal to 0, and therefore probability of A intersection B is also equal to 0. Such event is called mutually exclusive event. They are not interfering with each other. And 11th definition is collectively exhaustive. Collectively exhaustive elements. A and B are two events in sample space, then A union B is a sample space. So A and B put together exhaust the sample space collectively. So A intersection A dash is empty and A A union B is sample space, A intersection A dash is empty, collectively exhaustive. So all put together will exhaust the total sample space. Okay, so collectively exhaustive. A intersection A dash is okay. Mutually exclusive and collectively exhaustive. Mutually exclusive and sorry, हे इथे आता नसलं तरी चालेल. Collectively exhaustive means A union B are exhausting the entire space. Now 10 and 11 together, mutually exclusive 12. It is like you have total sample space and you have events which are subset. Because this is A, this is B, this is C, this is D, this is E, and this is F. So there are total 6 events in the sample space S. So A union B union C union D union E union F is a sample space. So collectively exhaustive. Their unions is a complete sample space. And A intersection B is empty, B intersection. So they are not having any intersection. Mutually exclusive. Collectively exhaustive. Okay, so these are two important. Okay, then I am supposed to do the definitions. I have done the proper ordering by spending 1 hour yesterday. Go to page number 2. Okay, now the theorems. These are the terms that we are required. Anybody wants any extra explanation on these terms? Now, addition theorem, first theorem. Addition theorem of probability. Very simple. Before doing addition theorem on probability, let us first understand if A and B be any two events in the sample space, then let us understand the meaning properly. A union B. Can you describe A union B in English? What do we mean by A union B? Occurrence of at least one of them. Now this is important because this will decide our calculations are correct or wrong. So occurrence of at least one of A or B is A union B. Second, A intersection B. Simultaneous occurrence of A and B. That comes, the element should be in A as well as in B. So A and B. So this is AND. This is AND. This is OR. Third, A dash. Non-occurrence of A. Fourth, A dash intersection B dash. What will we call this? Non-occurrence of A and B. Is it correct? Non-occurrence of A and B is A dash intersection B dash. And the last one, little bit confusing, but we should do it. 5. A subset of B. Occurrence of B implies occurrence of A. That is the meaning of these 5 terms which we'll have to keep using while doing set theoretic probability calculations. I wait for a minute. Okay, so if A and B are two events and we want to find out the probability of A union B, then by set theoretic calculations, something related to sets, if I want to find out probability of occurrence of at least one of A comma B, either A or B, is probability of event A occurring plus probability of event B occurring minus probability of simultaneous occurrence of A and B. This is what is addition theorem of probability. Now, if A and B are mutually exclusive, what does it mean? Mutually exclusive means they carry this is equal to 0. Then probability of A union B, probability of A union B is equal to probability of A plus probability of B. Simple. Probability of A dash is equal to 1 minus probability of A. Complement. Mutually exclusive and collect as mutually exclusive and collectively exhaustive. A and A dash are mutually exclusive and collectively exhaustive. Then probability of A dash is going to be 1 minus probability of A. Can we write down this probability of, can you show me probability of A intersection B dash? Is equal to, show me what do you think? Okay, as far as A intersection B dash is concerned, you draw a Venn diagram and find out what you want. We want this particular area in LHS, A dash intersection B dash. A dash is denoted by blue lines, B dash is denoted by red lines, and therefore we want A dash intersection B dash is probability of A minus probability of A intersection B. If we rearrange this, we get probability of A intersection B dash plus probability of A intersection B is equal to probability of A. Now find probability of A dash union B dash. We should do it exactly similar way. Do it and show me. This is 1 minus probability of intersection, because in the Venn diagram, suppose this is A, suppose this is B, then A dash is all this. B dash, B dash is all this. And we want A dash union B dash. So only thing we do which we don't want is this. Okay. Therefore, 1 minus PA intersection B is going to be the remaining part, because P A intersection B and P A dash union B dash are complements of each other, and they will make occupy the entire space. Next, probability of, now word problem, probability of P of, let me describe the event, exactly one of A comma B occurs. Is equal to, show me the answer. Exactly one of A comma B occurs, probability is probability of A plus probability of B minus 2 times probability of A intersection B. In other words, this is probability of A union B minus probability of A intersection B. And A union B, we have seen earlier that it is probability of A plus probability of B minus probability of A intersection B. So this and this is same. Next, if elements, 3 elements, A comma B comma C. If A comma B comma C are any 3 events, in the sample space, then addition theorem, P A union B union C is going to be equal to, write down, okay, this is kind of inclusion exclusion principle. So probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A plus probability of A intersection B intersection, include, exclude, unnecessary exclusion, therefore include. Good. Probability of, find this probability of exactly one of A comma B comma C occurs is equal to, easy. Check if you are convinced with this answer. probability of A plus probability of B plus probability of C. Add all three. Then remove. We have the experience for 2 earlier, so remove 2 times probability of A intersection B minus 2 times probability of A intersection C minus 2 times probability of B intersection C. So now you have to take care of the common area, which is plus 3 times probability of A intersection B intersections. Okay, that is what is exactly one of ABC occurs. Because why this factor? Because you have unnecessarily removed it thrice. We should add. And you can check by drawing your Venn diagram, and this is going to be the correct answer. Next, exactly probability of exactly 2 of ABC occurs. बोला P A intersection B plus P B intersection C plus P C intersection A, these three are added, minus we want exactly 2, 3 times P A intersection B intersection C. Okay. If you want any explanation for any of them, you can tell me. We can draw diagram and get the explanation. We can get it clarified. Next, probability of at least 2 of ABC occurs. I will just, meanwhile, I will draw the diagram for this one. Maybe for the first, the diagram will look like this. There is a sample space. There are 3 circles, A, B, and C. There is a common area. And then what you want exactly 1. So we want this. We want this. And we want this. This is the first diagram. For second, let me draw a diagram for second. What is exactly asked? If there are 3 circles, then you are required to show this one, and this one. That is second. And at least 2 of ABC occurs. So the last which is asked is, you have these 3 circles, 1, 2, and 3, at least 2. If you have 3 is okay, but at least you should have 2, and therefore your favorable area is going to be this, inclusive of the total intercept. So only difference between earlier and this is, instead of 3, it should be minus 2 P A intersection B intersection C. P A intersection B plus P B intersection C plus P C intersection A minus 2 of this. This gives you the at least 1. And then if there are 4, if there are 5, you can extrapolate and write down your answer. Okay, this is basic. This is what you had already understood and thought of earlier. Now let us make little more complicated. Okay, so how does probability of an event change with extra information? How does probability of an event changes with extra info? Okay, now this example already I have said, if Virat Kohli has lost three consecutive tosses, lose. So we are talking about what has already happened. Then what is the probability of he getting winning the toss in the fourth place? So I am giving you some extra information and trying to ask you the question. Actually, toss of a coin is half, always 50%. But then if you have some additional extra information about what has happened earlier, then this percentage of probability may change. That is what we are looking at now. What happens if extra information is available? Example, let me give you example. One, if you toss a fair coin three times, toss of a fair coin three times, and the question is, what is the probability of three heads? Question one, what is probability of three heads? Easy, 10 standard question. Let me write down the complete sample space. H, 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 T, H, T, H, sorry. I don't know how it should be written, but I am writing it some way. One T is done. Now H, T, T, then T, H, T, then T, T, H, and then T, T, T. So there are 8 elements in the sample space and only one is favorable. Therefore, the probability of 3 heads is 1 upon 8. However, if I ask you a question 2, suppose if we are told that the first toss was head, first toss was head, what should be the probability of 3 heads? Given this information, if first toss was head, what is probability of 3 heads? Okay, in this case, the sample space is different. It is not like this, but the sample space is H, HH, H, HT, H, TH, and HTT. This is your sample space now. And then you are answering what is the probability of 3 heads. The answer is going to be 1 upon 4. So we are putting additional condition and asking the probability question. It is called conditional probability. Something has already happened. Now you tell me what is the probability of this thing happening. It is different than otherwise asking what is the probability of an event happening. So if I want to show it to you geometrically, what we are discussing is these are the 8, maybe H, 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 T, H, T, H, H, T, T, and then remaining 4 are here. What? T, H, 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 no, T, whatever. Okay, remaining are here. T, H, T, 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 T. What else is remaining? T, T, H. Okay, so this was a complete sample space for question number 1, and you were looking for favorable, therefore only one of the 8 parts. However, first toss was head, that information is given to you. Now you are looking at only these 4, and the favorable is 1 out of 4, and therefore this is the conditional probability. So if I really want to put it in mathematical terms, what is conditional probability of conditional probability of event A happening given B? Probability of event A happening given B, it is written as, denoted as probability of A either divided by B, or it is also written as probability of A slash B, A given B. Probability of A given B. So what is the formula that we would like to have here? Probability of A, with the example that we have in hand, probability of A given B is probability of A intersection B, A intersection B. What was our event A in this case? Event A was, okay, let me write down the formula first and then we will discuss probability of B. Okay, and in our case, probability of A intersection B was, think about it. Event A in our example, event A. See, writing event correctly carries lot of importance in probability. Event A is all 3 tosses are heads. And event B is the first toss is heads. Okay. So what is the probability of event B otherwise? First toss is head, so it is 1/2. Correct? And A is all 3 tosses are heads, the probability is 1/8, and therefore probability of A intersection B, all 3 tosses are heads and first toss is heads, so A intersection B. Now how are you going to deal with this? How are you going to deal with this? So it is 1/8 upon 1/2. Is it correct? That is what is this answer. So whatever this formula that we are writing, PA intersection B upon probability of B is your PA given B. Okay. So if this conditional probability definition is correct and understood, then probability of A given B is equal to probability of A intersection B upon probability of B. Of course, probability of B should not be equal to 0. If probability of B is 0, then it does not make sense. A given B does not make any sense. But if probability of B is not equal to 0, then we get multiplication rule or theorem. That is, probability of A intersection B is equal to probability of A given B into probability of B. This is yet another important result that you have. Probability of A intersection B is probability of A given B into probability of B. Let us take one example and try to understand this in a better way. Example. I mean, this again can be written as, using symmetry, probability of B given A into probability of A. It is probability A intersection B. If you do it by saying that B happened, B, what is the probability of B given that A has happened, then it is probability of B by A into probability of A. Again, it will be probability of A intersection B. Okay, question. Draw two cards from a deck. Define events first. Event S1. First card is spade. S2. Second card is spade. Okay. Then what is S2, probability of S2 given S1? चल खड़ा हो गया. Now we can do this in two different ways. One, solving directly without bothering about what is the formula, etc. If the first card is spade and S2 is second card is spade. So what is the probability of second card spade given that first card was spade? Given that first card was spade, it is direct, because if the first card was spade, then that card is gone out of the calculations, and therefore only 52 cards are left, and out of which there are 12 cards of spade. Therefore, probability of second card spade is 12 out of 51 cards which are remaining. Direct answer. However, if we want to use this formula, what is our, we have to first find out probability of S1 intersection S2, which is either, first card is spade and second card is spade. This is first card is spade and second card is spade, which is probability of first card is spade, which is 13 upon 12. sorry, 13 upon 52. And because this is intersection, our English is and in combinatorics English and means multiplication. So probability of first paid 13 by 52 and probability of second card is spared, which is 12 upon 51. So PS S1 intersection S2 is this quantity. How much is this? 3 upon 51. बरोबर है 4 3 12. Okay, and what is probability of S1? Probability of S1 first card is paid is 13 upon 52, which is 1/4, and therefore probability of S2 given S1 is equal to probability of S1 intersection S2 divided by probability of S1, which is equal to 3 upon 51 upon 1 upon 4, which is equal to 12 upon 51. Now, this was simple. Therefore, we could directly visualize and get the answer first. However, in complicated cases where the wording is not leading to final answer directly, complications, therefore it is better to do it using formula, because set theoretic calculations we have found out how these probabilities we are going to get using formula. Okay, let me check whether you have understood. Okay, there are W white balls. Question. And B black balls in a bag. One ball is taken out at random without looking at the color of that ball. We have just put the hand inside the bag and taken out one, and is thrown without knowing THROWN, without knowing the color. Of the ball. Okay, you just take out once, close your eyes, take out one ball and throw. You don't know what that color was. And take second ball and take out second ball. What is the probability that the second ball is black? Now answer. Suppose I have a sample space omega and suppose I have, for time being, suppose I have 3 events in this sample space. This event is B1, this event is B2, this event is B3. So mutually exclusive, collectively exhaustive. So omega is B1 union B2 union B3, and B1 intersection B2 is empty. All that is available. Suppose mutually exclusive, collectively exhaustive, there are three sets, B1, three events, B1, B2 and B3. Okay, and there is one more event which is A, which is happening. Okay, now if I want to find out what is probability of A, I should find out this, correct? Then I should find out this, and then I should find out this and add them. That is going to be probability of A. So in set notation form, I can write probability of A intersection B1 plus probability of A intersection B2 plus probability of A intersection B3. If I add all these three intersection probabilities, then I will get probability of A. Actually, you can understand this. If you are not understanding this way, you can understand this by taking number of elements. Number of elements. And every time dividing it by total number of elements in the space omega, you convert number of element understanding into probabilities, but I am writing it directly right now. Probability of A, if I want to find out, it is number of elements in set A divided by total number of elements in the set total space omega. That is what is LHS, which is as good as writing probability of A intersection B, that means this area plus this area plus this area. Okay, three areas. And now we have learned how to write down probability of A intersection B1 in terms of conditional probability, that is probability of A given probability B1, probability of A given B1 into probability of B1 plus probability of A given B2 into probability of B2 plus probability of A given B3 into probability of B3. Okay, and if there are n events in the omega space, mutually exclusive, collectively exhaustive, then this chain, these additions will be n in place, sigma, all of them. This is called law of total probability. Okay, and now how is it going to be useful to us in solving the above problem? Is simple. Now let me make the diagram for the above problem in blue, because we are solving blue problem. There are only two events in the omega space. Two events. This event is first ball is black, and this event is first ball is white. However, you are required to find out second ball, probability of second. Probability of this event is second ball is black. Okay, so second ball is black. Let us call this event as A in our earlier notation. Let us call this as our first B1, event B1 and event B2. So we are interested in finding out probability of second ball black. So we are interested in P of A, which is summation of probability of second ball black given probability given first ball black, or probability of second ball black given first ball is white, because we don't know what is the color of first white ball. So I am translating the problem in English first and then we will write the mathematical version. So this is exactly what we are going to do here. Probability of second ball black given first ball black into probability of first ball black plus probability of second ball black given first ball white into probability of first ball white. Only two terms, so we will have the formula A given B1 into probability of B1 plus probability of A given B2 into probability of B2. This is what we are going to do. So probability of B1, this is easy. Probability of B1, first ball is black. What is the probability of first ball is black? B upon B plus W. And what is now the probability of second ball is black given first ball was black? Second ball is black given first ball was black. So out of black balls, first ball is black, which is thrown out, and this is what is this I am calculating. Second ball is black. How many balls were there remaining? B plus W minus 1. Correct? This is for the first, plus probability of second one is easy. First ball is white, which is W upon B plus W. This is always easy. And probability of second ball is black given first ball is white. So we have all the balls available. B divided by B plus W minus 1. Okay, so using formula, if you want to solve this problem, it is going to be like this, and then further simplification will lead to, surprisingly, the simplification will lead to B upon B plus W. Simplification will lead to B upon B plus W. Do you want to see that? Okay. Denominator both sides is same. Therefore, numerator is B square minus B plus BW divided by B plus W minus 1 into B plus W. Now numerator we can take out B common. Inside bracket B plus W minus 1 divided by B plus W into B plus W minus 1 equal to B upon B plus initial probability. If you are not looking at that ball and throwing it, the probability continues to remain as original. Next level of the problem is you are taking out one ball and throwing it without looking at it. You are taking out second ball, throwing it without looking at it. Two balls are thrown just like that. What is the probability that third ball is black? Next question. First is thrown. Second ball is thrown without seeing the color. Both without seeing the color. What is the probability of third ball being black? So calculate. Okay. So here there are first two balls are thrown without seeing, and the third ball probability being black is asked. So now let us list how many terms are going to come. First ball black, second ball black, third ball black, or first ball black, second ball white, third ball black, or first ball white, second ball white, third ball black, or first ball white, second ball black, third ball. These are the four cases. We want third ball to be black, third ball to be black, third ball to be black, black. So we have BB, BW, WW, WB. That those are the things which are going to happen before. So probability of third ball being black is equal to probability of first ball being white into probability of second ball being, sorry, probability of first ball being black into probability of second ball being black given first ball is black, and probability of third ball being black given first two are black. Okay, we should write it that way. So probability of first ball being black, B upon B plus W into probability of second ball is black given first is black, B minus 1 upon B plus W minus 1, and probability of third ball being black, B minus 2, because first two are already given to be black, B plus W minus 2. This is for this term, plus R plus B upon B plus W, first ball is black, probability of second ball white given first black, that is white, divided by B plus W minus 1, third ball is black, given first is black, second is white, B minus 1, because one black ball is less, and B plus W minus 2, they are removed, plus simple. First ball is white, W upon B plus W, second ball is white, W minus 1 upon B plus W minus 1, third ball is black, all black balls are there, B plus W minus plus last one, W upon B plus W into B upon B plus W minus 1 into B minus 1 upon B plus W minus 2. Surprisingly, if you simplify this, these denominator two factors, bad factors, will get cancelled, and eventually you will get, after simplification, the answer B upon. So for all practical purposes, doesn't matter how many balls you draw in the beginning and throw them, and you want nth ball to be black, probability continues to remain B upon B plus W. That is initial proportion. Initial proportion continues to remain same for nth ball also, provided you are not looking at the balls that you are throwing in between. This is surprisingly happening, and it is true, and it is by calculations it is happening. So whatever complicated expression that we will get this by simplifying the numerator, it will get factorized, and two of the bad factors in the denominator will get cancelled, and B upon W will remain, and then the numerator you will have only B remaining there. So this is interesting example because you are not watching the balls being thrown. If you are watching those balls being thrown, then it is simple problem. First ball is black, thrown. Second ball is white, thrown. Third ball is, what is the probability that third ball is black? Then first ball is black, second ball is white. Those are known to us, and then you will have this as answer. Second term will be the answer. If first is ball is black and thrown, second ball is white and thrown, and third is black. What is the probability that third is black? Then only the second term will be the answer in that case. But because we are not seeing the ball being thrown, all four possibilities will be there, and after simplification you will get the initial probability.